Our next topic of discussion is structure and activity relationship of drugs. This is commonly called as SAR, structure activity relationship. So actually, this is the relationship between structure of the drug and its activity. It is called structure activity relationship. For example, this is a drug. Okay, this is the drug is name is pattern 1, and you can see that this is reported recently in the journal, International Journal of Molecular Science. And you can see this drug, I can see this molecule. This slide is actually given to understand what is called structure and activity relationship. This molecule is having this ring. This is an aromatic ring. This is actually a heterocyclic ring. It's again an aromatic ring. And there is NH here, secondary amine, and there will be N times CH2 here that bridges the NH secondary amine and the aromatic ring. You can see that here, it is found that this nitrogen, heterocyclic nitrogen, it is very important for the activity of the drug. The drug is actually used to NEK for inhibitor. NEK is actually an enzyme. NEK for inhibitor is actually NEK for inhibitor. This drug, this nitrogen is very important for the activity. And it is found that this nitrogen is disadvantageous for activity. So if we replace this nitrogen by carbon, the activity of the drug increases. Now see that this is the NH secondary amino group here. This bridge is, this NH secondary amino group is very important for the activity, it's crucial for the activity. And you can see this is a side chain, CH2N times. If N is equal to 2, the activity of the drug dramatically increases. In this aromatic ring, you can call that to be ring A. Ring A. You can see if there is a R2 group here, and if the R2 group is methoxy, chlorine or bromine, the activity of the drug increases. In the ring B, aromatic ring B, if this is actually electron donating group, the activity of the group increases. So in a drug, there are different places where we have got substituents. If the nature of the substituents affects the activity of the drug, it can be represented by using structure-activity relationship. This is a simple example of a structure-activity relationship. I just want to show with an example. Thus, structure-activity relationship is the analysis of the dependence of the activity or the biological effects of a drug on its molecular structure. That means how the activity of the drug varies when we change the molecular structure. That is actually what is called structure-activity relationship. And you can see that molecular structure and biological activity are very much interdependent. And by observing these results, we can structurally modify the drug and bring desired effects. If we know that electron withdrawing groups is good, we can add a very good electron withdrawing group. And that means we can expect that activity to increase. Like that. So we can modify the structure of the compound if we know the SAR such that we will be getting more potent drug with less side effects. In effect, SAR is actually the relationship between the chemical or the drug or three-dimensional structure of the molecule and its biological activity. You know that the determination of chemical group or functional groups are responsible for evoking the target biological effect on an organism. So these chemical group, functional groups are actually taking part in the chemical reaction that will bring out the biological response. And there's another term called QSAR, quantitative structure-activity relationship, that we'll see the end of the lecture. You can see that here we quantify the results. Here in the previous slide, we have just mentioned that if it is there, it increases. If it is there, it decreases. That's actually a qualitative method. If we can express them quantitatively, it is called quantitative structure-activity relationship of QSAR. So, in effect, we can say that QSAR attempts to find a consistent relationship between the variation in the structure and molecular properties and the biological activities in a series of compounds, not in a single compound, but a series of compounds. In order to study SAR relationship, we should actually study a large number of compounds. Then only we can get an idea regarding SAR. Later, it is exploited to another set of molecules. Then we can get it quantitatively and mathematically. It is called QSAR or quantitative structure-activity relationship. And this is something called 3D QSAR. This is actually a very important method, and this is very much useful in the drug design. So, for example, it is the penicillin molecule. Okay, the penicillin system. You can see that here we are going to study the structure-activity relationship of penicillin. You can see that here it is found that first position, sulfur. Okay, so it is found that when the sulfur atom of the thiazolidine ring, is a thiazolidine ring, is oxidized to sulfone or sulfur dioxide, sulfur oxide, it improves the acid stability but decreases the activity of the drug. If the sulfur is oxidized to sulfone, the activity of the drug decreases. Now, this is the second position. Okay, if to get good activity, there should be two methyl groups in the second position. If one methyl group is replaced by another group, activity decreases. The second thing. The third position, we have got COH. COH is very important. Free COH is very much important for the activity of the penicillin. If it is converted to alcohol or ester, the activity is found to be decreased. The fourth position, nitrogen is must. If you replace by carbon and hydrogen, it will not go. And this is the fifth position. The fifth position, no substitutions are allowed. It's hydrogen here. If the substituent there, like CH3 or any substituent, activity of the drug decreases. Okay, it is actually what is called structure-activity relationship, and this is the structure-activity relationship of penicillin. The structure-activity relationship of penicillin. This is actually what is mentioned here. Okay, so we can explain in another way also here. Here we have seen only 5 important points. Now, there are more other points also here. You can see that here, this is very important. We have seen that this position is important. This free COH is important. There's a lactam. You can see this is actually beta lactam. You can see this is a lactam. This is a lactam. This is an alpha position, beta position called beta lactam ring. And the beta lactam ring is strained, and that actually leads to actually the activity. And if there is a free hydrogen here and free hydrogen here, there should be cis position. That's why we say that it should be unsubstituted. The cis position, then only there will be activity. Okay, so you can see that here, if there is a side chain, amide side chain here, acyl amide side chain is here, I can see that if the electron withdrawing group is there in this side chain, that will make the oxygen less nucleophilic. Okay, and bulky groups, if it is here, that inhibits the activity of the inhibitory enzyme beta lactamase. And if they have got more polar group, that will make the entire molecule hydrophilic. Okay, these are some of the structural activity relationship of the penicillin. One example that you have seen, SAR of penicillin. If you don't want to study, don't go through this thing, and you can study those 5 points. These 5 points are enough. Another compound structure-activity relationship that I would like to discuss you is morphine. Morphine is a very important drug. Okay, now we are going to see the SAR of morphine. This is the structure of morphine. Maybe knowing structure of morphine, you can see in the morphine there are 2 phenolic OH. And if this OH is removed, activity of the morphine is reduced. Activity of the morphine is reduced. And this is an ether linkage. It is found that if the ether linkage is removed, activity of the drug increases. Okay, now this is the second, this is the ring, A ring, B ring and C ring. The C ring, you can see that here there will be OH. If OH is oxidized, the OH is oxidized and this double bond is reduced. If the OH is oxidized to ketone and double bond is actually reduced, that means there will be no double bond here, the activity increases. Also, if this OH is replaced by acyl group, activity increases. That is called heroin. Acetyl morphine, it's called heroin. And you can say here in this position, if the H is replaced by OH, activity of the morphine decreases. Now here, in this tertiary amine bicyclic chain, if the N is replaced by methyl benzyl group, activity increases. And if the N is replaced by an allyl group, activity decreases. Actually, it acts as an antagonist. This is the structure activity relationship of morphine. So if you are asked to write about the structure activity relationship, you can write the examples of morphine as well as the example of penicillin. Now it's a time to study what is called QSAR. QSAR, as I told you before, is quantitative structure activity relationship. It's actually a mathematical relationship which correlates the activity, measurable, okay, with that of the specific properties of the molecule. There's a function, there's a relationship between activity of the drug. Activity of the drug should be a function of some parameters, for example, molecular weight, refractive index. Okay, then, okay, substitution, etc. If you make it quantitatively, that is called quantitative structure relationship. So, QSAR attempts to find a consistent relationship between the biological activity of the drug and the molecular properties, so that these routes can be used to evaluate the biological activity of the new compounds. Okay, and this is very good tool to understand the electronic effects, steric effects, and lipophilicity of the molecules. So, in QSAR approach, what we try to do is to identify and quantify the physiochemical properties of the drug. So, we see that any property will affect the biological activity of the drug. And based on that, we make an equation. And this equation is used to quantify the relationship and role of the property in the mechanism of the drug. And it is actually used to predict and evaluate the biological activity of unknown drugs. It is called QSAR, or quantitative structure activity relationship. So we just express them mathematically. We just express the observed system mathematically. We'll be getting QSAR. These are some of the molecular properties that we study in QSAR. Density, ionization energy, heat of vaporization, molecular weight, enthalpy hydration, pKa value, boiling point, refractive index, etc. Are actually used to study the biological activity of the drug. So here in QSAR methodology, we use several descriptors and they correlated. Okay, normally in QSAR, we at least use 3 to 5 descriptors. This is actually called QSAR. So we have seen in this lecture 2 very important methods called SAR and QSAR. SAR is structure activity relationship. It will just give you the quantitative idea of the relationship between the activity of the drug and the structure of the system. And in QSAR, what we do is that we study the mathematical relationship between the activity of the drug and several molecular parameters of the drug. This is actually called QSAR. Thank you very much.